So my name is Quincey Koziol. I'm with Lawrence Berkeley National Lab now, although I was with the HDF group for a very long time, about 10 years, and before that with NCSA for about 18 years. So I've been doing HPC, particularly focused on storage and I/O for about 30 years now, just for fun. About the last 20 or so of that has been working on HDF5, and I will give you guys an overview of what that looks like, an introduction to HDF5, and advice and hints and example programs and everything, how to do that in a scalable, high-performance way on today's supercomputers. I also really enjoy questions. That's great if we don't get through all my slides. I've got 105 anyway. I'm not getting through all of them no matter what, okay? So ask questions. Please, usually there's somebody else waiting to ask that question too or interested in the answer, and it's better to speak up and we'll have a little conversation. So there's a URL on the bottom of these things. It's also up on the presentation slides for the day, but the URL here opens a folder in Dropbox that has all my example programs in it too. This is on the bottom of all the slides, so you don't have to go crazy to get it right now. But it's there when you need it, and if you want to look at some of the programs in advance or skip through slides, and is he going to get to this kind of thing, it's all there. Very basic question, right? Okay, why do you want to use HDF5? Why might you want to use HDF5? We talked a little bit about files per processor. This is an incredibly intense I/O day. You've gotten some of the world's experts on storage and I/O to speak to you already. These are the people who know where all the bodies are buried, and by God, we might have killed a few of them ourselves, you know? So you've already asked yourselves, why do I want to do petascale I/O? Maybe I really don't want to know all the guts and gory details of Lustre and MPI, and where is everything hiding for you? And that HDF5, figure that out and do that, or PNetCDF or Adios. You want to do science, ultimately, in the long run, right? That's where your focus is. Let us be the storage experts and get the job done and just report bugs to us. As I say here, HDF5 principally focuses on optimized I/O to a single shared file, but we do have several explorations going on for not file per process, but sort of a M to N kind of situation where there's some files for all your processes. And I'll maybe get a chance to cover that in the later part of the talk. So as I said, we'll talk a little bit about HDF5 just at the big level. I'll try to get you familiar enough with HDF5 programming that you can kind of walk around in a program and understand basically what's going on to start with, and hopefully dive into more details, but there's a lot of APIs. We've been around for 20 years, and we like programming. And then try to get into some scalable parts of things as much as I can. That's where I'm going to try to keep us. So HDF5, hierarchical data format, version 5, and you go, version 5, that's interesting. What was HDF4? And you got, and like Rob was saying earlier, it was like, should not have used the same word, right? HDF4 is a completely different software package. We wrote the same thing, the package, right? And then we went, oh, there's kind of these limitations in it. We should redo it and extend it and blah, 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 blah. And we should have called it Zoltan or whatever you said, right? Because everyone thought, oh, no problem, I'll just up the version number. And it's like, no, totally different API, totally different file format, everything's different. Just so happens to be called version 5. So ignore that part, it's HDF5. It's designed to have an open file format, so I will not talk to you about the file format spec. It's online. People have reproduced it from the ground up in Java and all kinds of fun things. So I do know that the file format spec is correct from a black box kind of perspective. And we'll mainly focus on the software itself and talk initially about the data model so you have some familiarity with the concepts. Although Rob's talks earlier with kind of multi-dimensional arrays and things like that are very much applicable here too as well. So HDF5 in a lot of ways has some components of XML. It's designed to be self-describing so that once you get an HDF5 file, you can use tools or the API itself to query into it and figure out, oh, look, there's 42 data sets in this file, and they're all three-dimensional except these two, which are two-dimensional, and dimensions and the underlying data type for the elements. Everything else is there. Very, very rich, extensible file format. It's also designed to be a replacement, hopefully, for binary flat files. Very high performance. We try to add as very little overhead as we can on top of things while giving you all the benefits that I've been talking about here. So it's designed to be compact and scalable, just as like your Fortran write call, right? In some ways, we do occasionally called HDF5, you know, the PDF for science, right? It's a standard exchange format. All the information that you'd like can be bundled into there, images and arrays and annotations and a hierarchical structure and text and, heaven help us, MP3s, all kinds of people have done crazy things, right? So you can put everything you want into this container and portably send it around to other people. In a lot of ways, you'll see this, it's a lot like having a file system in a file, so it's hierarchical. It's actually a graph, but you can make complicated things and shoot yourself in the foot, so start simple with hierarchical collections of things. In a lot of ways, too, it's like a database, right? You can do random subset access in a high-performance way. So it's not exactly like any of these things, but it has strong components from all of them, and we try to put them in a way that is useful for the scientists and the applications on these big machines. And in other places, too. I mean, people have ported HDF5 all the way down to feature phones, which was entertaining email, you know, all the way up to, you know, of course, supercomputers here. So it's designed for high volume, complex data, every size and type of system, like I say. Feature phones, really, Nokia called us. Flexible, efficient storage and I/O. You can organize things in however you'd like. You can put your own data model in there, although I do encourage you to use, like Rob was saying, something that's standardized for your science community. Try not to invent too much on your own. You want other people to read your data too, right? One of the primary focuses for HDF5 has been to support this long-term data preservation. NASA uses HDF5 for some of the storage for their weather and climate monitoring satellites, and they'd like their data back in 50 years, you know, so we'd like to give that to them as well. It does occasionally skew our perspective of, I'm sorry, your feature just isn't important enough for us to stick in the software, right? You know, because it's a little weird, and in 5 years we know it's not going to matter anymore. So we tend to focus on a bigger, longer-term kind of thing sometimes. But there's a very, very large HDF5 ecosystem. Many, many, many different commercial and open source packages use it. Many different agencies in the federal government and internationally. Lots of different wrappers and everything, books and everything that have been written about it. I wanted a question. You're supposed to give me a question.
I was just excited about the Raspberry Pi.
Yeah, it's crazy. They do this thing. Right. This is exactly right. It's like I say, feature phones, you know, Raspberry Pis, whatever. We used to support VMS. You want some fun? High-level conceptual view of things. Let's start with the HDF5 data model. So HDF5 files are containers. They hold a variety of data objects. And together, those are designed to be sent around or viewed as a science output, a science package, a container. There's several different major interfaces. We'll talk about these three on the left, datasets, groups, and attributes. And within those, there's some underlying concepts, links and data types and data spaces we'll cover as well that are kind of supporting these other three major kind of classes, in a sense. We implement this in C, but we try to be at least somewhat, as much as we can be, object-oriented. Starting with the most fundamental thing that you probably want to store in HDF5 is your multidimensional array. And in HDF5, we call this data set. So they organize and contain your data elements, the array. You can see that there's two components to an HDF5 data set. There's metadata, this leftmost portion of things, right? Specifications about the array and the array. So the array is scale, right? Gigabytes, terabytes, as large as you like. If you get over 16 exabytes, I got to tweak the file format a little bit, but it's okay. I haven't seen a file system that large yet anyway. So, but the metadata is scalable, small, tiny, and usually hundreds of bytes to accurately describe whatever your array looks like. In this case, a data set has two fundamental aspects for describing the array. It needs a data type, which is what is every element in your array, right? What kind of thing it is. And this one I'm using an example that it's a 32-bit middle endian integer and a three-dimensional array. What is the data space, the arrayness part? Three-dimensional 5 by 4 by 7. And you can see that we organize these things. Oh, I got it backwards. I had it the right way, and then I thought, oh, it's wrong. The slowest dimension is your first dimension, and in this case, it's 7. It's like Z, right? This one's right. The second fastest dimension is 4 in this case, Y, and the last dimension will be the fastest in C, right? So that one should be 5. Data spaces describe the logical layout of elements. You can have null data spaces if you just want an attribute that just says, hey, this is a tag on something, and I don't really need any data associated with it. So if my data space is null, there's no elements. You can make scalars that act like zero-dimensional points, kind of in an array sense, just a value. Or, as I say, the most common one here is a simple array. It's multiple elements in a rectangular array. We do allow another extension against, say, the NetCDF data model is that the number of elements in each dimension, any dimension you want, as many dimensions as you want, can be fixed or unlimited. So you can have arrays that have 2 unlimited dimensions, or 3 or 20, whatever. But fundamentally, at its core, it's an array, and you're just extending it if you want to extend the dimension of one of those, or the size of one of those dimensions. So as I say, there's 2 roles for the data space. We describe the arrayness, but we also use that arrayness to say, hey, within here, I want these elements. There's a selection within this data space that I'm interested in doing. So this is a one-dimensional 10-element data space, and it has a selection that starts at element 5 and is a count 3 elements long, right? I'll show you some more complicated ones in a little bit. Data types, this is the flip side. You can think of data sets as kind of a cross product of a data type and a data space. They describe the individual data elements. They're homogeneous. All elements are the same data type. You can have integers, floats, enums, and a lot of things, right? Most people are really interested, of course, in your integers and floats. Enums, you can say red equals 2, green equals 3, blue equals 4, whatever. You can define each element within an HDF5 data set as an array if you're storing vectors or matrices, as an array element in your data set. NASA actually stores 12-bit integers. So, people deal with 16-bit floats sometimes in the video industry as well. So these are not wacky things, and HDF5 has the extensibility to encompass those things. Caution you a little bit about variable length types. We support them just fine, but it's never been a focus in HPC. So they work just fine, but they're slow and not particularly good on HPC systems. So if you're thinking, oh, I'll just store this 4 GB array of strings, it's like, probably not a good idea to begin with. And secondly, it's not going to do I/O super fast, okay? Compounds if you want structs. Good enough to get started on here, but there are a few more. Fastest dimension is 3 at the end, then 5. It's flipped in Fortran. You describe it the same way to HDF5, and the data gets stored in the same way. And canonically, we store it in the file in the C order. We don't store some data in Fortran order and some in C order. We lie to you in Fortran. And if you define this in C, what Fortran would tell you is the dimensions were 3 by 5 the Fortran way, right? And as if it were stored on its side, but the fastest dimension the Fortran way. A little bit more complicated definition for a data set, still 3 by 5. So the data space is the same. We have the same number of elements. The type within each element is different, right? This is a much more complicated data type. So it's a compound type. It's got several fields, in this case 4. 16-bit integer, unsigned 16-bit integer, a character, 32-bit int, and then one of these array types. And each element here in the array for the fields in the compound type is a float 32. HDF5 will gladly let you create arbitrarily deeply nested data type definitions. So you can have compound data types that have variable length sequences of array types whose elements are compounds that have whatever you'd like to do. We've got some wonderful tests. You can go look at them. Yes, sir?
So dimensions could be unlimited. Is there a default way of handling that?
I'll show you a little bit. We require the data set to be stored in a chunked fashion so that you can extend it properly. And when you create the data set, you define the dimensions, the maximum dimensions, and you tell it, hey, you know, it's the same or fixed in these two dimensions, but I want it to be unlimited in this dimension, and then you extend it to make it bigger. There's API calls to extend.
More than one unlimited dimension?
Oh, sure, yeah. You just kind of tell HDF5, make it this big, or allow people to write to it as if it were this big, right? And then we allow writes into those regions as if it were that much bigger. So, okay, fine. I've got a data space. I define that. I define my data type for an HDF5 data set. And what does that look like in the file? In memory, almost always, you're dealing with just a regular contiguous buffer, right? You may only have a subset of the data in the file as your buffer in memory, which is very normal for parallel computing, right? But these are the three forms of storing HDF5 data sets that are supported in parallel. I'll show you some in the next slide that are not supported in parallel. I should probably put it on the slide, sorry. So by default, you think, oh, well, I just create an array in the file, and it's so big, I just go allocate 4 meg in the file, and there you go, boom. That's a contiguous storage. That's the default. If you don't do anything special, and you say, hey, I want this data set, it's 1,000 by 1,000, and each element is a 32-bit integer, you'll get a 4 meg contiguous data set in the file. Now, if you want to do subsetting from your processes, or you want it to be extensible, you can define your data set to be chunked in the file, and then the chunks have to be the same size, and each chunk is kind of stored independently in the file. So if you tell me that you had 1,000 by 1,000 data set, but you want the chunks to be 100 by 100, still 32-bit ints, you'll end up with 40,000 byte chunks. 100 by 100 times 4, 40,000 bytes on disk for each chunk. Now, if that lines up nicely with your division and labor in your application code, you win really nicely. I'll show you why as one of the example codes later. Because you can just read all the data from one chunk in one I/O call instead of skipping across the contiguous storage in the file. But I'll show you some example codes about that as well. And if you want to compress the chunks, I'm lying to you a little bit here. There is a way to compress one contiguous chunk, but I'm going to gloss that. You guys should, I'll leave that for you to discover. If you do want to compress your data, for whatever reason, you have to use chunking. Let's just say it that way. And of course, you can extend chunk data sets just as well. So the other three ways, these are not supported in parallel, at least not currently. If you've got a very tiny data set, and it's important to you for your data model that this is stored in HDF5 as a data set, or it just happens to be small in this iteration of your application or whatever, you can store that array, the array elements, directly up into the data set object header in the file. Where all the metadata normally gets stored, that couple hundred bytes I said before, you can just kind of jam the data set elements right alongside it. So it gets read in one I/O request. Hey, I get the metadata and the raw data all in one I/O into memory and cache it. And then whenever you do access on that data set, you're actually reading on the memory directly. Only works for very small data sets, obviously, because you don't want to accidentally cache a gigabyte. External data storage for HDF5 files, we've had this occur in a number of times where you have some legacy data sitting on disk somewhere, but you'd like to treat it like it was an HDF5 file, but it's just Fortran writes, binary files that somebody else created, right? So you kind of want to put a wrapper of HDF5 around that says, here's all my metadata, attach some attributes to it, and make it compatible with the HDF5 ecosystem, rather than shoving these binary files into it. You can point at your external stored binary data from an HDF5 data set that's stored in the header. And then when all the HDF5 operations just kind of happen the way you think they would. We actually jump over and we access your binary file for you, but it all looks like an HDF5 file, and it feeds into the nice visualization and other HDF5 tools chain, right? In a kind of similar way, virtual data sets are a way of saying, hey, I've got this data set in another HDF5 file, and I want to compose them together in a way that looks like one big HDF5 data set. This comes up a couple times for like mite sources and other X-ray source kind of scenarios. They've got cameras, they're pointing, or effectively cameras, right? Imaging systems that are pointing at some subset of the sample that they're imaging, but there's 6 of them, right? And they think of that as one frame, but there's 6 different streams of images that are coming off of this thing. So they store it as 6 different data sets, and then they compose those into one virtual HDF5 data set that builds all those together. And then again, the HDF5 ecosystem looks at that virtual data set and says, oh, it's fine. It's one big data set. I do reads and writes, and it all works the way it should. HDF5 attributes are metadata, user metadata, right? You say, hey, when did I do this run? How many processes did I use? What was the date? What was the machine? What was the compile configuration? What's the startup parameters? All those kind of things. You want to attach those or decorate your HDF5 objects in some way. They're very similar to key values. Each attribute has a unique name for that object. So you can have the same attribute name across a lot of your objects in your file. And a simple value. It's an array, just like data sets are, but they're small. They're designed to be, as I say, metadata, lightweight things that you attach to another object in the file. We don't support partial I/O on them. You can't compress them. You can't extend them. They're just kind of a little block of data that says, hey, I compiled this on, this system at this date. Groups and links is where I usually lose a couple of people, but, well, you can do complicated things. And I like them, but then they get complicated, and most of the time you don't need them in an HPC environment. But, so if you have an HDF5 container, you don't just kind of want to let it throw a whole bunch of data sets in the file without any structure to them. What you want is some kind of grouping or hierarchical structure for the data in the file. So typical file system kind of layout, everybody starts with a root group in the file somewhere, and then points at objects that are in the root group, and those can be data sets or groups. I only show groups here, but you could easily have a link to this data set as well. And then everything comes out much more nicely and more coherently, more structured, rather than the old MS-DOS, everything is in the top directory, right? So there's a couple things here I'll mention. One is that you can have hard links from several groups to point at the same object in the file. So it's really a graph structure at its root, right? And so this data is not duplicated. Instead, you just have the symbol, hard links to the file. You can put attributes on the root group or any other object in the file. Like this one says it's timestep. You can point with your links to an HDF5 object in another HDF5 file. It's an external link. So you can build together many HDF5 files and just kind of point at all of them. Some of the guys for finance do this. They take a new set of stock tick data every day, right? And they put all that in one HDF5 file. But then they also have what they call a master file, right? That every day in the root group for the master file is a date that points at one of these gigantic tick data files. So they just create a new file every day, and then they update the one group with the root group with a link into the new file in the master file, and everybody gets to see the new day all at once, right? Nice way of stitching together many HDF5 files in a different way. So I'll talk more about software, but data model, any questions more about data model?
Yeah, so I'm thinking like SciViz.
Yeah.
And I see this and it says time step, 36,000. So that's like the traditional paradigm where every however many time steps you output your data, and then you load it back out afterwards and you visualize it all.
Yeah, sure.
So as SciViz is kind of going toward in situ, does this still play a role, or like how do they?
HDF5 itself doesn't have an in situ framework natively. It's storage and I/O software. It's I/O middleware. There are a few in situ frameworks that do support output into HDF5. Adios Dataspaces is the big one. There's probably other frameworks I can't think of right now, but and Adios has an option for storing data in HDF5. But if, reproducibility and some of the other aspects, eventually you need to store data somewhere at some point. That's where we generally stay and have traditionally built our strength, right?
It's not the SQL.
It could be. It's not, but we have a project that it's like the second to last slide. If you look at my deck, there's a little blurb in there that says query and indexing. And there is an effort as part of the exascale computing project for the DOE to build a query interface on top of HDF5 containers. And it's not SQL. It's what I would call more programmatic. So you build things up with function calls instead of text. But you can get there. Yeah. SQL doesn't understand arrays. There's some extensions to it and everything else like that, but they really aren't well standardized or very popular. So, and it also really doesn't understand hierarchical paths super well. So you'd have to really kludge stuff together. And I gave that a thought for a while and then decided that we'll just give people a programmatic interface. And if you want to make a text, processor on top of it that looks like SQL, great, go for it, So I copped out, kind of. Anything else? Go to software? Oh, yes, ma'am.
What's the benefit of having all these different pieces of data linked in the same individual file instead of just making a directory that has all of the different pieces organized in the same way?
It's a good question. So the benefit of having everything in one package is that conceptually, from a science perspective, all these things go together for some reason. These are, the input parameters for my simulation. These are the three different aspects: pressure, temperature, and density at this time step, and whatever else complex set of scenarios that you have going on in your science that says this all goes together in some way. And when I give somebody access to that, or I share it, or I archive it, or whatever, you're implicitly saying this all goes together. And you don't have to know that files A, B, C, and D in this directory over here go together, and this is what they're doing, right? So there's more structure around it, more self-description, and more long-term archiving capabilities about it, I'd say. So software. If you want to go grab the latest version of HDF5, this is the home page for the HDF group. As I said, I was at the HDF group for about 10 years. I was one of the founding guys who spun it out at NCSA. And they're a nonprofit organization whose mission is to sustain, develop, maintain, support HDF5 for the foreseeable future. So that's where we try to focus all the software goes back here-ness of things, right? It's the structured wrapper that is independent of federal agencies and for-profit commercial people that holds HDF5. So the source code's written in C. There's a lot of it. There's like 350,000 lines of code in the library. Like I say, we like to write software. There's Fortran, C++, oh golly, Python, Pascal, COBOL, Ada, Perl, R, you name it. Somebody's written a wrapper for it in HDF5, Ruby, just for fun, .NET, all kinds of things, right? So there's like 1,000, literally, if you go onto GitHub and you search around for things that are built on top of HDF5, there are 1,000 other packages that build on top of HDF5. The core set of software that we distribute here from the main repo, command line utilities, I'll talk about a few of them for doing kind of fairly straightforward but integral and important parts for HDF5. If you download the pre-built libraries, you can kind of look at them. There should be this libsettings file that you can see what compiler, what features were chosen, all these kind of things. And there's some compression libraries that come with the default pre-built binaries, just kind of heads up. But most of the time you're going to go on to Theta or something and you're going to say, link in HDF5 and use the header file. That's what you should do. So somebody gives you this HDF5 file and you go, I don't know. the guy at Argonne told me it was a container and I should be able to dump it, right? So try H5 dump or H5LS. They have a little different focus, but they do a lot of the same things. They'll give you the structure and the contents of an HDF5 file as kind of a text overview so that you can get an idea, what is this thing? Hopefully somebody told you more than here's this HDF5 file. But if you'd like to build simple HDF5 programs, well, you can build complex ones too, but most people don't want to roll the HDF5 compiler wrapper into your big science application somewhere. But if you're testing and writing things and you don't want to remember all the header files and libraries to include, H5CC wrappers act just like the MPI CC wrappers. They just grab the HDF5 stuff and put it in there so it links nicely with your source code. There's a very nice Java viewer and hundreds and hundreds of examples, I believe, and lots and lots of examples in all kinds of languages. Oh, I forgot Java before. So we all like layer cakes in software, right? This is sort of what the one for HDF5 looks like. There's some kind of twisting, turbulent behavior internally, but it's very close to this. Generally speaking, you're dealing with the API level, of course, and principally with these major data model objects that I talked to you about at the very beginning. There's support pieces in there, like I say, for dealing with data types, data spaces, the IDs that you get back for objects and things like that in HDF5, and then all the properties that you can tune and tweak about the I/O and the behavior of the objects in the HDF5 container deal with properties. Properties are a lot like MPI info objects. They're a way for you to kind of inject parameters through a standard API and still have some control over the behavior of the internal guts of the operations. There's a lot of internals here, but there is a bottom layer that we deal with that's public and pluggable. If you feel like writing a virtual file driver, that's great. A standard POSIX one for doing serial I/O, you can actually split your data into, here's my file for metadata, here's my file for raw data, which is sometimes very valuable because the behavior and the I/O characteristics for metadata are quite a bit different than raw data. Many file systems would like you to kind of do small random reads in one file and big, long, bulk I/O in a different file rather than get it confused. Yeah, but the standard one we're going to be dealing with for parallel applications is the MPI I/O driver. Talk more about that. As Rob mentioned earlier, the NetCDF4 API is built on top of HDF5. So when you grab NetCDF4 from Unidata, you'll grab NetCDF4 plus HDF5 and put that layer cake together for your application. So when you're programming HDF5, as I said, there's a lot of bindings. IDL, I forgot IDL before. We tried to impose some level of discipline in an object-oriented sense. When we started writing this in 1996, C++ looked sketchy, right? It really wasn't really standardized. People in HPC would run and scream in horror if you said, I'm going to write an HPC application in C++. They were like, no, so everything was written in C, right? We didn't want to go back to Fortran, but C was doable. So all the interfaces begin with H5 something, right? And the something is kind of like the class. So all the data set interfaces are H5D something. Files are F. Data space, can't have two Ds, so S for space. There's a lot of API routines. I kid you not, really 300-400 of them. Most of them are some property that tweaks a behavior of something where somebody in a particular aspect wanted to deal with things, or they're kind of all the methods wrapped around an object. Here's all the ways to deal with links in a group. And there's H5L, and there's like 12 or 15 routines that deal with links and groups. But it's not terrible, right? The examples are there for you to look at, and you can say, oh, okay, I really only need to know 6 or 7, maybe 10 routines, and I can get up and running and get simple HDF5 stuff out the door. Conceptually speaking, it's very C-like. You open the object, you access it, you close it. You have to do explicit initialization, explicit release, right? There is no scoping in C that lets me garbage collect stuff or anything like that. If you want anything other than the default behavior, you define that with properties in the property list that you pass in to HDF5. So here's a very simple programming outline. We create a file or open it, create a dataspace, H5S for dataspace create, right? We create a data set, or maybe we open the existing one. We read or write, close things up. Explicit opens, do something with it, explicit closed. Infinite number of ways we can make this more complicated, but really, if you want to get data in and out of HDF5, about 7 calls will do it for you. Other things you'll probably see in your first set of, I want to know how to do this in HDF5, take a look at these routines. If you want to do a subset, a selection within an HDF5 data set, or I'm sorry, a data space, you're going to select a hyperslab, like a regular set of blocks in an array, or elements, kind of points all over the place. And you want to query the data space back out of a data set that's on disk already as get space, right? So data types, if you want to create something that's a little different than one of the standard predefined ones, commit allows you to kind of store a complicated data type that you've already predefined in the file. Close, get rid of them. These things equal. You do get into this scenario with HDF5 where you retrieve a data type from the file, H5D get type for a data set, and you go, well, is that really the same? What is this? Is this a 32-bit integer? Is it the same as integers on my machine? I'd like to make certain that I know what's going on with the type on disk and the type in memory. And so one of the nice, convenient ways is take a look at this get native type. It says, whatever this type was originally, give me an equivalent type for this machine, right? Big Endian, little Endian, 32-bit, 64-bit, haven't helped you 16-bit. It gives you the right thing, the right definition for an array read or whatever you need to do to say, that will be an equivalent form on this machine. Groups, create, open, close. They're just containers that hold links to other things. Attributes, very simple, 4 or 5 API routines will get you through everything. Property lists, these are the most likely ones you're going to deal with, creating and closing them, setting chunking on a data set to define the subsets as for storage, and deflate or one of the other compression mechanisms on that data set. Probably your first bunch of HDF5 programming will cover what was on the previous slide and this one. About 20 or 30 API calls will get you pretty far. So that's all fine and fantastic. Now we get into HDF5 in parallel. You all know enough to be dangerous by now. That's really load up the big guns. I've probably been doing this already, but some of the terminology through the slides, especially in the parallel section. When I say data, I say sometimes raw data or data set elements. It's the problem size arrays that you're dealing with for your science data. Metadata, there's a lot of metadata that we throw around. Typically, when I say metadata and there's a problem with I/O and metadata, I'm talking about the internal versions of the file format and things like that that are HDF5 metadata. Your app metadata is usually your application form of things is attributes, and that's what you should be thinking of primarily as your metadata. But you'll see why I'm trying to be more specific here in a second. Talk a little bit more about these layers of things. It's 30 years, well, 20 years of programming on this, right? 300,000 lines of code. There's a lot of stuff I don't talk about. There's a lot of interesting more features to HDF5 that isn't strictly, what I can cover in 75 minutes or whatever in one tutorial. Lots and lots and lots of more information I can help you out with how to use HDF5, or I have this problem, or I have this interesting idea. Come chat, that's great. When we say parallel HDF5, we mean MPI parallel. There's, thread programming is common enough these days when people say, oh, it's parallelized, right? So no, we mean MPI parallel. Well, I know. It does come up though, HDF5 can be built to be thread safe. There's a tiny bit of overhead, so some people don't want it, but most of the time you do. It's built to be thread safe, and if you're using threads, it is thread safe, but importantly, not concurrent, okay? Only one thread can get into the library at a time. We put the big lock around the API, the source code, right? The code, not the data, which in retrospect was a very bad idea. It was really cheap and easy to do, very bad idea in the long run. because now no one can concurrently get in with multiple threads. What we should have done was the hard thing, which is lock each individual data structure individually and let multiple threads come in and do the right stuff. But that's a lot of work, honestly. So anyway, if somebody starts talking to you about multi-threaded HDF5, you have to remember, oh yes, multi-threaded, safe, but not concurrent. So you're only going to get one thread in the library, and whenever it finishes whatever it's doing and leaves, the next guy can come in. Another part of this I'll mention here is that the files that you create really are just straight out the same as a serial HDF5 file. There's no binary difference whatsoever. You can move them around between your laptop and the supercomputer, or different computers. They're all just fine. So we looked at this before, right? Create your file. The reason why you create a data space and not a data type is because there's lots of predefined data types that are really useful, like float, right? A 32-bit float on this machine. I can define a macro or equivalent macro that says 32-bit float and let you run off and go do stuff with it in your program. But I got no idea what your array size is, right? So, you know, there's an infinite number of 1 by 2, 2 by 3, 4 by 7, I don't know. So you have to define your data space. And as long as you use one of the HDF5 predefined data types, you don't need to create your own. So that's why this looks this way. More layer cakes, we like layer cakes. Typical, your application is running spread across the compute nodes, right? But they all call into an HDF5 library internally, and I'll tell you why that's important, because you're going to be making collective calls for high performance. So they all have to do things in a concerted and coherent way. We leverage MPI and only MPI right now, right? That is how we do parallel I/O. I was kicking some ideas around with Rob, and he's like, well, what about, you know, global arrays? And I'm like, yeah, I know, but I don't got time to go retool everything for global arrays. So everything relies on whatever MPI can give you right now. And like Rob was saying earlier, every so often I send him a really gnarly problem. And I say, I did the thing you told me to do, and it broke, man. And he's super. He goes off and fixes it, so it's nice. Underneath MPI, right, it deals with one gigantic, sometimes, HDF5 file that's stored in your parallel file system, and there's complicated stuff going down in the storage file system that you don't want to know about, right? And that's the whole point of using MPI and HDF5 or PNetCDF or Adios. But you don't want to know about the gory bits in the middle. The red things here are additions to your standard HDF5 programming example. I'll show you this a little bit more detail in a minute. Generally speaking, as we said before, you create your file, create a data set, and then write your data. If you're doing that in parallel, of course there's some MPI init somewhere, right? You need to be able to tell HDF5 that, hey, by the way, I want to open up my file using the MPI I/O driver and give it a communicator and an info object that it can use. Most people are using like ComWorld and info null, right? That's fine. And you don't have to worry about if it's yours or whatever. We'll dupe it inside and then keep our copy and keep going on with things. Then proceed as normal, right? And you say, oh, but I really want the high performance thing that Quincey told me about, and I want to do collective I/O. So you have to change your standard H5D write call, and normally this would just kind of be, say, default over here for the transfer property list. But in this case, you want to say, hey, no, I don't want independent default behavior for I/O. I would like to do collective I/O. And this is how you set it up. You create your transfer property list. There's other settings, other properties that you can set in there. But in this case, we're going to say, hey, no, my next call, or whenever I use this transfer property list, you can make many calls with it. I want you to do that using collective I/O. And then continue on with your program, right? Similar vein of things. As I said, we're gonna use that communicator that you give us, open the file. We copy the communicator internally. We give you back a file handle. And then you got to deal with that HDF5 file handle. It's kind of like a file object or whatever object-oriented sense. When we say all the processes must participate in collective I/O, really mean it. That's what that means, okay? There's an infinite number of support questions. They're like, I did the thing and it went zumba, 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 clunk. And I don't understand, man. So I'll show you what happens when you don't do it all together collectively, right? You do different things. If you want to use two different communicators, that's fine. Just open the file with two different communicators. It's all fine. And this is sort of the collective call gospel document, right? Anything that modifies the structure, like the groups and the attributes, the sizes of data sets, anything that modifies those parts of the metadata, the user visible metadata in the file, you have to do it collectively. I'll show you what happens when you don't. If you want to write elements in your data sets, you can do that independently. You can even, if you're very, very careful, open the file with write access from two different things and update the data set elements from two separate jobs. I do not recommend that because it is very dangerous and you will shoot yourself probably. But you can do it. There's a lot of other tutorial examples on the web here. What I'm going to do is jump out and at least show you what happens when you don't write your data out collectively or you don't modify the file collectively. So this is probably a little hard to see, but in that Dropbox directory, this is H5 par ex2a and 2b. Okay, there's only 5 of them. 2a and 2b is what we're dealing with. And I put it up here in my source code diff tool to show you that really there's only 2 things I care about that are different here. And I'm going to ignore the variable that's the for loop. On the left, you can see that the groups we create are dependent on the rank of the individual node that is running, right? So it gets a different named group on every rank. Group 0, group 1, group 2, group 3. I run 4 processes for the example, right? And in a perfect world, this would be fine. And in fact, I've got some funding from DOE to fix this, to make this work, all right? But for 20 years, because the original systems that we were running on, they did not so nice things to you. They didn't let you set aside processes. Everybody got cranky with you if you took one of their processes, because there wasn't a lot of processes, one of their MPI ranks. There was no threading, right? You could not run a server, do anything else like that. So you had to do everything within the model of one MPI application kind of working together. And I didn't get a chance to have anybody off to the side managing changes to the file and coordinating and doing server-like stuff. So everybody had to do stuff together. This is why we ended up with this interface where you have to do things together. So for this example, this will be a Zumba Zumba clunk, and this is a Zumba Zumba zoom, okay? So in this one, we say, hey, we're going to create a bunch of groups, one for each rank, but we're going to do them all together, collectively. Everybody goes off and creates a group called group 0, and they create a data set in that group. I use the group ID here, so we're inside that group, and then we loop back around, create another group, group 1, but everybody has to do it. It's really annoying, sorry. If you run the left example, the A example, the bad example, you get a file that only has one group in it. You're like, wait, man, I created 4 groups. This is the output from H5LS, there. I told it to do a verbose recursive dump of the file that we created here. So it says there's a root group, but there's only one other group. And in fact, it's group 1. It's not group 0 or 2 or 3, right? It's group 1, group 1, 1, right? Because at the end, some process has to write out its metadata, and if all the metadata isn't identical in all the processes, somebody's overwrites somebody else's. And I have a strong feeling this file is corrupted in other ways. So if you do this, you're probably going to have a problem. But in this case, when you did the bad thing, you ended up with one group, and it was a strange one, not even group 0, with one of the data sets that you created, but not what you wanted. And if you go off and you go run the B example, so this is the file from the 2B example, although I accidentally named it 2a.h5. And you can see in this case, it's got the correct data sets. It's got a group 0 and a data set in it, and a group 1 and a data set in group 2, and a data set in group 3, and it has 4 ranks, right? So when you modify the metadata in an HDF5 file, you have to do it collectively or bad things happen. Not only can you get files that are just like, look like they're corrupted or something strange, I didn't get all my output, but there's places in HDF5 where we assume that everything's identical in all the processes, and if you put enough data into the metadata caches, then it will try to synchronize those metadata caches and it'll hang because it has different amounts of metadata between the ranks, and your application will just go doot and stop forever, right? Sometimes one rank will keep going, and you're going, well, you know, but everybody else has stopped, right? So either you get a corrupted file or everything stops. Like I say, I would like this to be different, and we have funding to make it go, but this is where we're at right now. Sorry.
So you're going to dump data into these groups? Is this the idea? I mean, so each processor will dump it into just
Right, each process would write its data into one of these data sets or something.
3 that is free on each processor.
Yeah, something like that. Okay. Somebody else? I thought I said? No? Oh, sorry.
Is the close statement synchronized between different APIs?
Is the close statement synchronized between the?
Act as a barrier.
I'm sorry, what was
Does it act as a barrier after?
No, it does not act as a barrier. Certain caveats. You should treat it as if it were collective. HDF5, there is a thing in C where you can do an add-exit call that says when the application is about to leave, give me a callback, right? So we register this add-exit callback as a safety measure inside HDF5, and we'll try to shut everything down when your application is closing down. But you might have confused things sufficiently that we cannot fix it anymore. So you should treat it as if it were collective and try to close everything in the nice programming manner. Oh, I'm sorry. Yes?
So for this HDF5, so those functions are written already like from that. Okay. Have you ever compared like one application explicitly written like MPI IO and compare like which HDMI? So for which one is better?
I have a slide coming up. I'll show you the performance comparison for HDF5, MPI, and POSIX. Yes, sir?
So when we write the data in parallel, do we have to re-extract the data in parallel?
No, you can do whatever you like.
So there's no like a format saying we wrote the data in parallel?
No, the file is identical. The eventual file that you create is identical between a parallel application and a serial application. So you can take a file you created with serial and open it and modify it in parallel. And in fact, a lot of people do that as a workaround for this all collective metadata thing. They create a skeleton file with a serial program really fast, right? Because they're not storing any raw data elements in it. You just create the skeleton of everything, a million data sets or a million groups or whatever, and then close it in serial, reopen it on all your parallel processes, and then go dump out your data in there. It's a very reasonable pattern for programming with HDF5 in parallel. Yeah?
So HDF5 does not have the same meaning for collective as in MPI, right? Because in MPI we don't loop over the rings. Because everyone will arrive at the same function call and do the same thing, like a reduce or broadcast.
No, we use the identical definition for collective. I mean, when we say collective in HDF5, it means the same thing as collective in MPI. So if there is a call that must be called collectively, it must be called on all the ranks. It's the same. I mean the same thing here. What's the difference that you're seeing?
Because you need to loop over the rings.
Well, that's why I said that all the metadata modifications, in this case, creating groups, are collective. So in this case, this is supposed to be collective, but it's being called independently. Each rank calls it with a different set of parameters, right? I mean, technically everybody calls it, but they call it with different parameters. It's like setting up a bcast with different roots for the bcast, right? So if you put different parameters into your collective call, you don't have a collective call. So over here, we've got identical parameters into our collective calls, and that's why it works. So it's a little more subtle than I just called it, but you actually have to call it with the same parameters.
So each processor has groups 0 to 3 in this case.
Yeah.
Each processor.
Yeah. Which is annoying. I agree with you.
But on the terminal, when you did your thing, we only saw
That's the good one, right?
Okay.
Yeah, so that's the correct one, and that's why you see 4 here. There's group 3. I'm sorry about the escaping the spaces. That's just how the output looks. Group 3, group 2, group 1, and up there, group 0. Right, so there's 4 groups because we looped over 4 ranks to create the file.
Well, I was expecting to see 16.
16.
Oh, okay. So which processes groups are you printing?
Well, I ran this using 4 ranks, right? So I used 4 processes. So over here, my MPI size is 4. So everybody participates in that group create. So it acts like a single group gets created in the file, not 4 for that collective call. It's like a broadcast or something else in MPI. There aren't lots and lots of broadcasts happening. There's just the one, right? Yeah. Okay. Okay, this is good. Who else?
The logical size and the actual allocation size in your screen in the command line.
Let me see.
The command line icon code.
This one?
Yeah, logical bytes and allocation bytes.
Yes. Yeah, this is how many bytes are allocated on disk, right? It says I reserved space for 7 million bytes, right? Yes. And I actually allocated, my definition says that I should have 7 million bytes, and I actually allocated that space in the file, because we do lazy allocation normally in HDF5 that says, you can define all the data sets you want, but we don't actually reserve and allocate space in the file for that many bytes. So you sometimes you'll run a HDF5 program to create a skeleton file, and it's like 2K, right? And then you do H5LS on this file that you created and say, oh, well, it's like 8 zillion logical bytes and 0 allocated bytes, because we haven't created the actual data set storage for it yet. In parallel, it always allocates it. Anytime you do an HDF5 program, it will have a logical size that corresponds to your data set dimensions and your data type. And it will also allocate it so that we know exactly where it is for all the ranks in the job. It's another aspect of the metadata must be done collectively. I mentioned before earlier that you create one HDF5 file and it gets sent to the parallel file system, and that's actually composed of lots and lots and lots of hard drives or solid state flash things these days. So there's this striping going on underneath your file, right? And HDF5 doesn't always line up with that. There's good ways to make everything line up, and they're in the parallel examples on the web there. I don't talk to it. I don't have enough time to talk to it here. But HDF5 also has this funny metadata thing, right? So not only do you have to have some room to describe your data type and your data space, whatever attributes you have, and then allocate your data set data, and that gets striped. But when you chunk your data sets, there's actually the object header has a piece of it that's the chunk index, right, to look up where those chunks actually got stored on disk, because you can have lots of chunk data sets and they can get scattered all over the place. Object header, chunk index, pieces of chunks, they don't even have to be in the right order from your perspective, right? They just, wherever the space was available in the file, they get allocated, and that's why the chunk index looks them up. And then all that gets striped out over the parallel file system. And then I send bugs to Rob, and I say, your MPI Datatype didn't do the right thing. So there's a lot of complicated moving parts that you really don't want to do in your application program to get all the benefits that HDF5 and the other high-level I/O middleware gives you. But we wrestle with some problems for you to make that work and work reasonably highly performant as much as we possibly can. So just a little bit of nuts and bolts piece to it. Collective and independent I/O, touch on it again here. And kind of to reiterate, MPI says that for a collective call, all the processes of the communicator have to participate in those calls in the same order. You can get effectively deadlocks, right? If you call them in the wrong order, if on process 1 you call A, I don't know, bcast, right? And then a different bcast or an all reduce or something. If you call bcast and all reduce and then bcast and all reduce, you're good. if you call bcast and allReduce and then allReduce and bcast, you're probably going to get a deadlock in your MPI application. And it's very, very similar in HDF5. If you flip the orders of your collective calls in HDF5, somebody will get confused. Either we'll confuse MPI by sending on some communication pattern in a reversed or out of order scenario, or your data is just going to get confused inside HDF5's caching schemes. And I'm a little snarky here when I say independent aren't collective, but really, a collective call is not guaranteed to synchronize your program. There may not even be any communication. It might just set a bit in the communicator that says, yeah, I did that. I have some information so that the next thing when I need it, everybody has the same kind of piece of information. So a collective call in MPI and in HDF5 is an opportunity for that programming library, HDF5 or MPI, to take advantage of the fact everybody is here, but it may make a decision that you wouldn't necessarily expect. It may not do any communication, it may not synchronize, but you have to pass through them. It's kind of just like a set of gates that you have to pass through. Everybody has to pass through it in all the ranks and all their applications in the same order. So just kind of a helpful MPI programming thought, right? Typically metadata is small, you can do independent. If you really want to open up a group on one rank and open up a data set in there and do some reading in there independently, perfectly fine. You can go off and go do that set of metadata things for reading. Well, as I say, modifying must be collective. A lot of this is advice for how to tune your HDF5 application. All right, so this is the other example I have. And this is a while. So this looks like a little bit of a toy problem in a way, but you can just scale it out to today's, gigabytes instead of megabytes, right? Or terabytes, heaven help you. Application team report and say, this long skinny data set I have to find. It's pretty narrow. The number of ranks I have isn't very high, but they each have a column in this thing, and I want to do the I/O, right? Okay, fine. So they say, well, each MPI process is going to write to one of those columns. It's a pretty simple data type, so it's a pretty small. In a very, very small, I kind of flipped a little bit between 1,000 and 230,000, sorry. But there's a small amount of I/O, and when you scaled this problem down to be really tiny, still it's kind of a long time, right? 32K, and if you made it a little bit bigger, it was like getting worse in the linear ways. It was like, this is bad. So something was very, very wrong. And so if you want to debug things with HDF5, turn on the debugging, right? Build your own HDF. Many of the systems have a debugged version of HDF5 that's installed, but if you need to, HDF5 builds very easily on most systems. I run it on my laptop all the time to kind of debug problems and do things like that. Turn on the debugging, and then you can set this environment variable that says, hey, I kind of want to see what MPI operations are happening to my disk when I'm doing my HDF5. And you'll see something that says, hey, for this example code, and I'll show you the code in a minute, this is the super block getting written out, and it's better now, so ignore that part. But you say, hey, wherever this data set is located, I see a lot of these 8-byte writes, and there's a lot of them. And it's like, I thought you guys said that you were really efficient, and you wrote out big streaming block bulk I/O, and it was all great. And I said, well, yeah, except I gave you a shotgun, and you put your foot in front of it, and you got a problem. So what's happening is each process is writing one element, and then skipping down to the next row, and writing another element, and skipping down and writing, and skipping and writing. It's like a gazillion I/Os that come out of this one I/O call that you made in HDF5. Okay, so let's look at the source code for that, which is the one on the left is the independent version. Very straightforward, independent, contiguous data set, very much like the slide I just showed. And the one on the right would be a better way. So if you run the 1A example, this is very straightforward HDF5 code, right? I've shown you all this. You set your file access property to this to be MPIO. You use that when you open the file. Close the file access property to this because this is C. create your data set, I'm sorry, your data space that describes the dimensions, create your data set, tell it, I didn't describe this in the last piece of code, but you have to tell it how big your buffer is, right? Otherwise I got no idea where your elements are in memory. On each rank, we select a different column. So each column here in our application is dependent on the rank. So rank 0 writes column 0, rank 1 writes column 1, and then there's a buffer in memory that corresponds to that column that we're writing. And if you do that with the environment variable set, you get exactly what you expect. So, HDF5 was so awesome, why is it writing out millions and millions and millions of IOs, right? So, well, I don't know what you told me to do, but you told me to do this, right? You said, independently, I want to write out this column, and I don't have any resources to make this better in any way. Every process is on its own. They aren't able to communicate with each other because, whatever reason, you told me to do this independently. Write this column out. The only really coherent way to do that is go write the column out individually. We can't go get a block of the data from disk and update it with our elements and then write it back, because we're going to overwrite the other process's job of doing the same thing. Each one gets a copy and updates their column and then tries to write it back. They're going to overwrite it, right? So I got to do it just the elements you told me to write. The solution to this is what you might expect to say, well, he keeps talking about this collective I/O thing. So what if we wrote that data, everything else is identical, but instead we're going to use that data set transfer property list with the collective set, and then we put it in here in our data set write call, because over here the default is independent, and then I clean up, right? So if you run this, hey, that worked just about the way I thought it would. These look a little funky. The size is 1 because we're building an MPI Datatype and we're passing it on down to MPI on each rank. And so everybody's got the same offset, and you can kind of tell it's a funny looking thing. So when these happen, that means that there's an MPI Datatype that's getting passed into a file write at all, and one I/O operation happens as a result. And of course, the file will be identical, but we've given all the information we could to MPI to say, hey, do this in a nice optimized way. And of course, you get much less I/O to your file system. I'll show you one other way to make this better. You could, if you knew that all these things are nice columns like this, abuse the chunking notion in HDF5 a little bit and say, well, every process, he told me that the subsetting thing works really well if you're going to do subsets to from each rank, right? So I'll make my chunks be a single column, right? And then when every rank writes its own piece of data, it'll write one chunk, and we can do that. So that's what this definition in the 1C source code says. It says, hey, this is identical to the independent version, right? 1A up there, except we set up chunking. So we say, I want a data set creation property list, a DCPL, and I want to change the default properties, which is contiguous, so that it's chunked. And I set the chunk dimensions to be those long, skinny columns, and then pass that on down here when I create the data set instead of the default, so it's not contiguous anymore. And then I just go ahead and I do the independent I/O again, right? So in this case, you get roughly the same thing going on. Each process, which is why there's 4 of these guys, where'd my other guy go? Oh, they're here. Each process wrote out one big block to each chunk, its chunk. So you can say, that's probably pretty close to the MPI performance for a collective I/O. MPI is probably a little better, especially if the data sets are bigger and the I/O pattern's a little more complicated. But you can kind of sometimes twist chunking to your advantage by making it line up directly with whatever your processor is going to do I/O on, and go do your I/O that way. And it's kind of like the same idea as file per process, except you get everybody going into one file as a result. You have one private space that you're just doing I/O onto, one chunk per process in a way. Does all that make sense? Any questions about that? Yes? No? Yes? To define how the chunks are distributed to the processes?
Yes, but because I am thinking that perhaps you try to, if the file has some structure, kind of structure, for example, a file of MATLAB, and some array corresponds to a certain process.
Yeah.
You have to read that structure first, and then separate the data.
But you can query the data set and say, is this data set chunked? And then you can say, what's the chunk size? And oh, the chunks are 50 by 50. Could I make that work out for my application? Right? If it's a checkpoint restart, it's really easy because you created it and you should be able to make that work. Yeah. But
if you want to make the application flexible, for example,
right.
and you have a checkpoint, and you have a certain number of processes that you, when you restart, you don't restart with the same number.
Oh, I know. Yeah. That's hard. The best thing I can do is pick a nice number for your chunk sizes that would be flexible for a future restart with a different number of processes. Yeah.
What I do, for example, is, I don't know if that is right, I made every process to ascribe the complete file.
No, you could do that too, sure. Oh, one thing I would do well, we should talk more later, but I want one more warning and I got to wrap up so that Phil can get started. Sure, I mean, happy to talk, but just running out of time. Never ever make your chunk size 1, please, okay? Do not make chunks 1 element. The HDF5 library will be fine. It will go, okay, and the index to find each chunk will be bigger than your data set elements, okay? Right, because you're telling me that every single element gets its own place in the file, right? And I got to keep track of all those little elements in the file. And I/O is going to be absolutely horrid. Your file is going to be huge. It's going to go down in flames. It will work, but you will chew cycles like you wouldn't believe, right? So don't ever make your chunk size 1. And then people go, the next question is, well, how big should I make my chunks? And my answer is, I got no idea, man. It depends on your application, right? I don't know what you're doing. This guy writes columns, somebody else writes, rows, squares, I don't know. If you kind of want a general idea, what I tell people is pick the square root of your dimension in each dimension. Try to make them kind of cubic-ish, right? Cubes that you're writing out that are roughly equal. So roughly the square root in each dimension gives you a decent place to start. If you got 100 by 100, make them 10 by 10. 1,000 by 1,000, 35 by 35 is a good place to start, kind of, right? Maybe you want 50 by 50, something bigger or smaller, but it's like it gives you kind of a middle ground, a place to start for your chunk sizes, unless you know better, and never ever make them 1. You asked earlier about performance between MPI and HDF5. Each column here, there's this nice H5 perf tool that comes with HDF5 distribution, and you can run that to kind of check chunk sizes and data set sizes and what if I do this and that. You can see that generally speaking, MPI is about that fast, and HDF5 is a little bit slower, but not too much usually. And in many cases, it's fast. Both are faster than trying to do POSIX straight out. Okay, so this is a nice benchmarking tool for you to kind of play around with what if I set up my data sets like this or that. And we use it kind of as a cross-check to say, we would really like to keep HDF5 performance at 90% of the underlying layer. In parallel cases, it's MPI, and in serial, it's going to be POSIX of some sort, right? The underlying file system. So
H5 also character from MPI.
Yeah, it gives you all 3 numbers. So you can check in any one there, all 3 together, whichever you like. One final blurb, we're working on a bunch of exascale things. And literally this is just a tech zoo of terms, right? But there's a lot of interesting things we're working on for making asynchronous HDF5 calls, working around this collective metadata problem, single writer, swimmer, single writer, multiple reader, I/O on a file so that light sources and things can update a file and readers can be accessing it concurrently as it's getting updated. I mentioned earlier the querying and the indexing stuff, wrappers so that you could read a real .cdf file netcdf file or adios file. Lots and lots of things. Come talk to me. Final questions you have?
So I work with a team of astronomers and they use FITS files, and it would be a huge problem for them to rewrite, even though this would probably be better. So what would be the sales pitch to them to switch over?
Tricky problem. The best maybe thing, if you had a little bit of resources to put at it, you could make a wrapper to read FITS with HDF5. It's going to be some effort, but you could do it. Kind of prototyped it out a couple times. It's a tough job. Like I say, really have tried to engage with the astronomy community, and the astronomy community has rejected the transplant numerous times. Sorry. You can kind of use external storage in HDF5 too to make your data set think it's, or your application think it's HDF5, but then point at the FITS thing. Also could work. You can talk to me some more. I got war stories and suggestions. So if you want. Anyway, anybody else?
So you talked about compression, I guess, a little bit in one slide you mentioned.
Yeah.
So is there any, I want to clarify if there are any compression tools inside HDF5 so that we can have a compressed file. And second is that I know that there are external compression packages that works with HDF5. And I use one of them and I'm not sure why they're there. So.
There are a few compression interfaces or modules, plugins for HDF5 that ship with the library. There's one built in for deflate, which is libz, like gzip, and also a library that NASA likes called szip. And then there's a couple of other I/O filters in there that help compression in some ways. But again, we wanted to do storage and I/O work more than we wanted to write lots and lots of compression filters that were tuned to yours and yours and yours problems, right? So we made it a kind of an open interface that anyone could write a compression plugin and then allowed people to do that. So that's why you see a bunch of them, and they have different applications and specialties in various ways.
How does HDF5 writing on a massive supercomputer scale in general? I haven't looked at any performance numbers. I mean, it depends on the network and the disk. But
it does.
Modern architectures, how good do those things scale?
With careful tuning, like not just naively plugging away at stuff, right? With some careful tuning, you can typically get very close to the maximum bandwidth of the underlying file system. I could show you a quick slide we did a little while ago with an older system at NERSC. So if you look at these sets of slides in the deck, it basically was maxing out the I/O system on Hopper, one of the supercomputers at NERSC. It was a few years ago, but still. Configured correctly, this was producing ridiculous files, right? 350 terabyte files. The file system, people did not like us. They're like, you did what? I'm like, well, you know. So anyway, it certainly can, when you're dealing at that scale and you're taking over the machine for a while, things break, not just software. So it's a big endeavor that you have to ramp in carefully if you really want to get out to that scale. But it can be done.
Would it be always free?
Well, yes, I think so.
I saw HDF group and has other non-free version or something.
The HDF group is a non-profit, right? And they don't charge for open source software. And programmers do not eat air. So there has to be some way of monetizing people, right? I mean, somebody's got to pay to keep the puppy going along, right? And as much as I've tried within the DOE and NSF to really get them to be a cyber infrastructure piece that like maintained important software packages, MPitch and HDF5 and PETC and just nice things. I really haven't got any traction with that yet. So yeah, they're trying to find HDF5 or the HDF group. I think at the moment it's got a new CEO and he's still trying to figure out exactly where to put his feet. Okay, so occasionally he makes a misstep. What he's trying to do is the right thing: develop a sustainable way to keep the core software free and open source by building on some forms of paid services and support contracts around that. So the goal is to have an open core that's HDF5 and that all the stuff I've been talking about today, stay open source, well supported, continue on forever, right? But in order to do that, you got to charge somebody money for something because programmers got to eat, man.